Bassam Fayad and Raphaël Krikorian, both from Paris, both former students of Michel Herman. Bassam Fayad is directeur de recherche à l'Institut de mathématiques des Chaussures Paris-Rive-Gauche. And Raphaël Krikorian, he's a professor at Université Cergy Pontoise. And, well, they will talk about some results and questions about KAM theory, small denominator phenomenon, I imagine Hamiltonian dynamics, quasi-periodic cocycles, and all those kind of stuff. Let's appreciate his work.
Thank you.
Okay, so thank you very much. So we are very pleased to be here. So it's a big honor for us to be present in front of you. And we're going to talk about some topics in quasi-periodic dynamics. So the title of our talk is Quasi-periodicity in Conservative Dynamics. So maybe I have a plan. Oh, it's here. Okay, so there will be basically two parts. So the first part would deal with the Hamiltonian dynamics. And we will discuss topics around stability, so in various senses. So we will first discuss elliptic equilibria and the generalization for an invariant quasi-periodic tori. And then we will discuss three types of stability. So there will be the topological stability, KM stability, which means existence of many invariant tori for a Hamiltonian system, and effective stability, which basically means Nekhorochev type stability. And then we will discuss the problem of the divergence of the Birkhoff normal form. So the Birkhoff normal form is a very important tool in Hamiltonian dynamics. And then we will go to pseudo-rotations, which is a very particular type of Hamiltonian system. And then we will discuss several topics there on mixing and reducibility, basically. Okay, so first we're going to start with the notion of equilibrium of a Hamiltonian flow. So let's take a C2 function, H, from the 2D dimensional space, R2D, to R. And we assume that H of 0 is equal to 0, and the derivative of H at 0 is equal to 0. So then this function H defines a Hamiltonian flow. So x dot is equal to dyH, and y dot is equal to minus dxh. And so in that setting, 0 is a fixed point. And we will denote the flow of this vector field by phi th. And so this flow preserves the origin. So I just noticed that it's a symplectic. So for each t, phi th is a symplectic diffeomorphism. Oh. And so the problem is to study the stability of this equilibrium. So stability in which sense, we will see. So first, in the most basic sense, so we are looking at the topological stability of this equilibrium, which means basically Lyapunov stability. So by symplectic symmetry, the topological stability of this equilibrium is possible if and only if the eigenvalues of the linearized system are pure imaginary. So I won't write the equation, but so that's what we have. And the form of H in that case would be the following. So the H, the function H, which I will call the Hamiltonian, so the Hamiltonian H, has the following form. So with the laser, here maybe, no, here, okay. So H of xy is the sum of real numbers omega j times yj plus a cubic term. And so the ij are quadratic terms like that. So we will say that the equilibrium is non-resonant when the coordinates of omega are rationally independent. So similarly, we can define similar things in a quite closely related situation. we take a C2 function from Rd times Td. Td is the d-dimensional torus. And we look at the differential equation, Hamiltonian differential equation. R dot is equal to d theta h, and theta dot is equal to minus drh. And for this kind of system, we can define the notion of invariant torus. So in that case, the torus 0 times Td is an invariant torus by the flow of the Hamiltonian. And the dynamics on this torus is a translation by frequency vector omega or omega t. So here it's the flow has frequency omega. So more generally, so we will say that T is an invariant torus for H. If T is diffeomorphic to a torus and invariant by the flow, we will say that the torus T is Lagrangian if, furthermore, it is a graph, a Lagrangian graph, so of the form of this form. Lagrangian means that the graph has this form with the gradient here. And we will say that the torus is quasi-periodic if the restriction of the dynamics of phi on T is conjugated to a translation flow. So now we can discuss the notion of stability, and we will discuss three notions of stability in this talk. So the first one, maybe the most, the oldest notion is certainly the topological stability in the sense of Lyapunov, which means basically you say that an equilibrium is stable if you want to stay in the fixed neighborhoods of 0, you have to start close to 0. Then there will be Km stability, which means the existence of invariant objects. So Hamiltonian systems have natural invariant objects when they exist, and they are, most of the time, they can be tori. And Km stability will be to prove the existence of many tori, invariant tori. And the third notion of stability is the quantitative notion, which is the notion of Nekhorochev stability, which means that, okay, so you take an initial condition, you iterate the system, and you will stay close to the origin for a long time. And you want to say, okay, if I want to stay epsilon close to the origin, or epsilon to the power a, I can be close to this equilibrium for a long time, which can be, in general, exponential for analytic systems. So, we are first going to discuss the notion of Km stability. So, we say that a torus T0, or the torus we had last time, so basically we have this thing. Voilà. So, our system has this form in action angle variable. Voilà. So we say that T0 is a Km stable torus. So I will discuss first the case of equilibrium. If in any neighborhood of T0, the set of quasi-periodic tori for the Hamiltonian flow is of positive Lebesgue measure. So in that sense, when we say that there are many invariant tori accumulating T0, it's in a measure theoretical sense. You've got a stronger notion, which will be the notion of being of density 1 at 0. So if you look at the measure occupied by these tori, they have density 1 close to the torus T0. So the problem is then to study the topological Km or Nekhorochev stability of a non-resonant elliptic equilibrium or of a quasi-periodic torus. And so this will be the problem we are going to consider. And in all this problem of stability, there is an important tool which is the Birkhoff normal form, which basically allows you to take your system in a nice form and in very close to some integrable form. So Birkhoff normal form, so we assume that H is like, so again, just Maybe we should have put something, but okay. So I recall you that H has this form. So you've got here this part. So we said that the Hamiltonian is integrable if you don't have the big O here. Then the notion is purely quasi-periodic in a whole neighborhood of 0. So if you have this term, O2 of R, you can just say that this is T0 is an invariant torus. If you remove this term, then all the torus, every tori are invariant.
Or
So
if you take it independent of theta, independent of the
yes,
angle.
but in that case, it will be omega will be, they will have the same frequency. But more generally, well, we could consider more general situation. Okay, so we have this form. And so what is Birkhoff normal form? So we take this kind of system. And the thing is that for any n, for any integer n, you can find a symplectic change of coordinates, let's call it Zn, and a function Bn, which would be a polynomial, such that you can conjugate the Hamiltonian. So this is a the notion of conjugacy for a Hamiltonian. You can conjugate it up to an arbitrary, up to an error which is of order 2n plus 1. You can conjugate it to an integrable form. So this is for any n. So I assume that omega, the coordinates of omega are rationally independent in that case. I will say a little bit more. And in fact, if the function is C infinity, so if H is C infinity, then you can take n is equal to infinity, and then you find a formal Z, which will be exact symplectic in the formal sense, and a formal B infinity, such that H is conjugated to an integrable form. So this is basically the Birkhoff normal form. So just one further remark. Yeah, and B infinity will be called the Birkhoff normal form. So remark, so in fact, in the preceding slides, I was discussing the case of equilibrium. So if you consider the case of an invariant torus, omega has to satisfy a stronger condition. And this condition is an arithmetic condition, a so-called Diophantine condition, which has this classical form. So you can define in that case also Birkhoff normal forms. And so once you have this notion of Birkhoff normal form, you can basically prove KEM type theorem. So I will just state one theorem, so which will be the following. So it's a theorem basically due to Kolmogorov, Arnold, Moser. There is the work of Russman, many people. And then we present here a version that we have with, so EFK. E is for Eliasson, Håkan-Eliasson. So which says basically that if you have, so let's consider the case of an elliptic fixed point. So if you have a Hamiltonian of this form, let's say that it's smooth, then if the Birkhoff normal form is non-planar, the origin is KM stable. So this is something that I'm going to say what means non-planar. It means that basically it is non-degenerate in the following sense, is that there does not exist a gamma, a vector gamma in RD, such that for any I, the gradient of B infinity, scalar gamma is equal to 0. So this is, in principle, a checkable condition. So you can, maybe you cannot compute B infinity. This is a very difficult task. But in many situations, in principle, you can compute Bn. And if you have, so for example, let's say that the derivative of, the second derivative of H is positive, is definitely positive, you will have this kind of non-degeneracy condition, and so the KM, this theorem of KM stability. So this is the story for systems we are Hamiltonian, which are C infinity. They could be also analytic. At this stage, there is basically no difference between the analytic case and the C infinity case. So now I will, Bassam will tell us
about
next.
analytic situation a little bit more. Thank you, Raphael. Let me continue immediately with topological stability for analytic Hamiltonians. So topological stability is the stability in the sense of Lyapunov. And there is a famous conjecture by Arnold that says that apart from two cases, the instability, Lyapunov instability of equilibria will be prevalent. So the first case is the case of very low dimensional Hamiltonians in 2 degrees of freedom. In this case, under the so-called isoenergetic non-degeneracy condition, we know that in any energy surface there are Km tori, and it follows that the equilibrium is topologically stable. The other case is the obvious one when the Birkhoff normal form is, when the omega i's in the definition of the elliptic point, I'm not going backwards, if they are all of the same sign, then the Hamiltonian acts like a Lyapunov function and the equilibrium is stable. You just have to see that the energy surfaces are ellipsoids, and therefore the dynamic is stable. So Arnold's conjecture is that apart from these two cases, equilibrium is unstable. Now, of course, to prove instability in analytic is harder than in smooth. You expect more stability for analytic systems. This is the line of thought of this presentation, and it's the reality. Instability was proven for elliptic fixed points in smooth category by Douadi, but he didn't show the generic instability. We have today a lot of activity on genericity of instability. There is some progress, at least for action angle systems like quasi-integrable Hamiltonians, but we still don't have the genericity. And what we really don't have is analytic results. So in analytic result, we don't have even a single example of an elliptic equilibrium that is non-resonant and unstable. We have examples that are resonant, but of course, resonant systems are more likely unstable, because imagine a fixed point that is resonant, and imagine a perturbation that pushes in some direction that is resonant with the symmetries of the rational point. So, of course, the dynamics will escape. And such examples, analytic examples that are unstable for resonant points, were known since 1901 by Levi-Civita. And then Cherry wrote a very extensive work on unstable resonant elliptic points in the 30s. But no examples are known in analytic, although we expect that the phenomenon is generic, but we fall short of proving any single example of instability. And so we have now an example, many examples actually, for arbitrary frequencies in 4 degrees of freedom. We can construct explicit real analytic flows that have unstable elliptic points. Now, these are not generic, but they do have a non-planar Birkhoff normal form. And this means they are Km stable. So we have the Km stability that coexists with the diffusion, which we expect in Arnold conjecture. So let me say that what kind of instability mechanisms we had up to now. We know of two types of instability mechanisms. The first one is the so-called Anosov-Katok. It's an instability mechanism that appears for degenerate fixed points, whereby you must imagine an integrable system that is a harmonic oscillator with a very Liouvillean frequency, and imagine you are in dimension 2 for a diffeomorphism, and you have the orbits are circles, and then you conjugate these circles and you make them wiggle. So the system becomes integrable but wild, because the orbits, instead of doing simple circles, they oscillate. And then you do more and more conjugacies, and at the end, you get an unstable elliptic fixed point. This is a Liouville construction. It can be made in Diophantine framework in higher dimension, but it is very degenerate, and it has, so the Birkhoff normal form is equal to the harmonic oscillator. There is no extra terms, it's just the linear omega I Ri. And the system you obtain is also rigid. It has iterates that converge to identity. The other diffusion mechanism that is known is much more robust, is the Arnold mechanism, whereby you have a sequence of normally hyperbolic lower dimensional invariant tori that have heteroclinic intersections and diffusive orbits. They are orbits that follow these chains of heteroclinic connected lower dimensional tori. And Dwadi's construction of an unstable elliptic point is based on Arnold's mechanism. And why is it so C infinity in nature and not analytic? Because he needs, the way we do it is you take resonant lines that converge to the origin and you build your diffusive orbits. But then for each resonant line, you need a compactly supported perturbation to diffuse along this line. And that makes the construction really C infinity. If you want to do analytic, you need to overcome the so-called double resonance change of resonant lines. You have to go through double resonances. And this is done, but also using compactly supported functions and very smooth in nature, as it is done today. So we introduced a new mechanism for diffusion that allows to obtain this in analytic with explicit forms. And it is not an approximation by periodic systems. It's more like an approximation by resonant systems plus perturbation. Like it's, you don't approach your system by periodic ones, but by periodic ones plus perturbation. That you don't get rid of the perturbation, actually. So for tori, you can do the almost usual Anosov-Katok construction and get topologically unstable analytic tori. Now, let me come back to the Km stability. Here again, the line of thought that says analytic implies stable appears here and shows you really how analytic is different from smooth. We have Hermann's conjecture that says that if the Hamiltonian is analytic, then as soon as you have just an arithmetic condition on the frequency vector, you have Km stability. So the strength of this conjecture is that you don't assume any non-degenerate condition on the Birkhoff form. Okay? This Km stability does hold for analytic systems in dimension 2, in 2 degrees of freedom. This was proven by Russman. And this shows how the low dimension is very special, even for smooth. So even for smooth systems in 2 degrees of freedom, Diophantine condition implies Km stability. In the strong sense, with density 1 of tori in the neighborhood of the origin. We made some progress in the direction of the conjecture, but we are far from completing it because we only prove that an analytic invariant torus is never isolated from other tori. We don't have positive measure. The way we prove this theorem with Eliasson is by doing normal forms with counter term, and we use analyticity in controlling the counter term and in showing that it is actually 0 on a set that is not empty. Okay. And just a slide about dichotomy here. So for smooth systems, you cannot expect anything like the Hermann conjecture unless D is equal to 2. So we proved with Håkan Eliasson, Raphael, and then with Maria Saprikina that in any dimension, in any frequency larger than 3 dimension, you have smooth examples of Hamiltonians that have non-stable Km, non-Km stable elliptic points. Okay, so this is in strong contrast with the conjecture. Okay, this shows you really that at some point there will be definitely a big difference between smooth and analytic, something that in Km up to now is not very common. Okay, as Raphael was telling you before, usually Km theorems are just technically a little bit different when you prove them in analytic or in smooth, and you have different arithmetic conditions. But here we're talking about different nature of behavior. Okay. Yeah. The examples we have of non-Km stable tori or elliptic points are still accumulated by Km tori. So one may hope for examples where the point is really isolated from any other invariant set. But there is a question by Perez-Marco that something like a hedgehog must exist around the fixed point. So nevertheless, it's a question, can you have no invariant tori in the neighborhood of the elliptic points? Let me end this part by talking about the effective stability. As Raphael was saying, it's a very natural physical question. How long does it take you to double your distance from the origin? Usually doubling your distance from the origin is the same time order of magnitude that it takes you to leave the neighborhood of the origin completely. In unstable systems, if you go from R to 2R, the time it takes you is like when you compute half-lives. It's the same as going to infinity. So the question is, what amount of time do you wait? For analytic systems, the existence of Birkhoff normal forms, and even for smooth, tells you that you must be slower than any power of the inverse of R. That's immediate from the Birkhoff normal form. If, in addition, you have an arithmetic condition, then you have control, quantitative control on the Birkhoff forms. And you get an Nekhoroshev-like exponential stability with an exponent that depends on the Diophantine exponent of the frequency. Moreover, you have the Nekhoroshev theory that tells you that generically in the Birkhoff normal form, or if you want, generically in the Taylor expansion of your fixed point. You have an elliptic fixed point. You take, it's an analytic Hamiltonian. You take the first d square coefficients of your Taylor expansion. Don't even talk about Birkhoff normal form. Just you have a fixed point, you have a Taylor expansion. You look at these coefficients and you say, what is the probability or what is the possibility that the point be very sticky, that orbits that start near the point don't leave fast the neighborhood of the point. And you ask this question as a function of these coefficients of the Taylor expansion of the elliptic fixed point. And it turns out that generically, so you look at the first d square Fourier Taylor coefficients, and you get a condition that tells you that if it is an open and dense set of full measure, if the coefficients are in this set, then the fixed point, the Diophantine fixed point, is double exponentially stable. So here, instead of this exponential, you get exponential of 1 over R. To do this, you combine the Birkhoff forms with estimates plus the Nekhoroshev approach with steep property of the normal forms. Anyway, you get this theorem. It generalizes a result by Giorgelli and Morbidelli, who obtain similar double exponential stability when the Birkhoff form is convex. So now we have a set that is of full measure and open and dense on the Taylor expansion of the elliptic point. So this kind of result can allow to specify a little bit the Arnold conjecture by saying that now we believe that generically elliptic fixed point is unstable and actually double exponentially unstable. Why double exponentially and not more? Because we, with David Sauzin, we recently proved that even when the Birkhoff form is convex, which is the most favorable condition for stability, we showed that the systems are not more than double exponentially stable. So we have examples that have definitely convex Birkhoff form that are double exponentially stable and not more. Okay? So we expect the condition to be optimal. And that's it. I just wanted to say that when we construct the unstable elliptic points, we didn't do the computation, but we believe the time can be proven to be exponential. So the time that takes you to leave the neighborhood R will be exponential 1 over R, which means that it shows that the Nekhoroshev estimate is optimal if you don't. So you see this estimate here. This is true under just the Diophantine condition. It doesn't depend on the Taylor expansion at the fixed point. no steepness condition. So if no steepness condition is imposed, we believe this is the optimal condition. One more thing, and then I let you, Raphael, continue, is that the examples of unstable tori, analytic unstable tori here, can be made in a way that the Birkhoff form is a polynomial. So this is curious, in fact, because when the Birkhoff form is, say, flat, equal to omega, then there is a theorem by Russman that tells you the system will be integrable. And here we're saying that this is not true if the Birkhoff form is a polynomial. Okay, there is no Russman theorem when the Birkhoff form is a polynomial. So the question of how does the Birkhoff form behave when a fixed point is unstable is a question asked by Eliasson. It's a long-standing question. Here we have examples where the fixed point or the torus will be unstable, but the normal form will be convergent because it's a polynomial. And now Raphael, I think, he wants to tell us something very exciting about the general behavior of the Birkhoff form. Raphael?
Okay, thank you, Bassam. Okay, so now the problem we want to consider is the problem of the convergence of this Birkhoff form. So I recall, so let's take H a real analytic Hamiltonian. So this H, so for this H, we have a formal conjugacy to an integrable form. So it is known since Siegel that this formal conjugacy in general is divergent. So this was proved by Siegel in '54, so which in particular implies that non-integrability is generic in some sense. And so there is a question raised by Eliasson. So he has been asking this question maybe for 30 years. So can the Birkhoff normal form itself be convergent if H is analytic? So, because you see this is a formal invariant. And so it defines a series, and you want to know whether the series is going to converge or not. So there were some, so there are some results on this question. So maybe the first result is due to Perez-Marco, so who proved in any dimension, basically, that if you take a non-resonant elliptic fixed point, you've got a dichotomy. So either the Birkhoff normal form is always convergent, whatever the non-quadratic part is, or it is generically divergent. Of course, you want to know so which parts of this alternative is true. If you assume that omega is very Liouvillean, in fact, so there are examples constructed by Gong of divergent BNF, but omega in that case is Liouvillean. And so basically you want to understand what happens in the more general case, and in particular when omega is Diophantine. So let's take d is equal to 2. If you have omega Diophantine, so in the set of real analytic Hamiltonian, the Birkhoff normal form is generically divergent. So in particular, you have this for any dimension. And this is also true not only for invariant elliptic fixed point, but also for invariant tori. So if you take a tori with the Diophantine rotation number, you can find examples of divergent Birkhoff normal form. So the proof exploits the analyticity of this H. So I'm not going to describe it, but just to say something. So when you've got an H like that, so you've got the Birkhoff normal form. So you take your Hamiltonian H and you try to conjugate it in the neighborhood of the origin to an integrable form. Okay, so there is an iteration procedure in some sense that does not converge. But basically, you have some quantitative results, more or less. On the other hand, you've got a more global procedure, which is a KEM procedure. So you take your age and you try to conjugate it more globally to an integrable form, so, which is basically what you always do in KEM theory. And that this is something you can do, but then when you do that, you've got resonances. And basically, these resonances make holes in the domain, in the phase space. And so the thing is that basically you want to prove that the holes are small. And in fact, that's what happens in this theorem. The theorem, in fact, if you assume that the Birkhoff normal form is convergent, then the size of the holes has to be smaller than what it should be for a generic system. So that's basically the way the proof goes. So of course you have then to prove that these holes are small. So I won't describe more of the proof. And I guess we go to, no, so yes, just, so there are also many important questions in Hamiltonian dynamics, even in low dimension. So for example, the metric entropy question is a very important question, and there are very little progress, apart maybe in a very non-generic case by Pierre Berger.
Touraev.
Touraev, thank you. Okay, so now we switch to another subject, which is the pseudo-rotations. So pseudo-rotations are very special cases of Hamiltonian systems. But so let's consider area-preserving disk dynamics. So by a result of Franks and Handel, you know that if they are transitive and have zero topological entropy, then they are special. So they are pseudo-rotations, which means that basically they have just one periodic point, which is zero. And that's normalization. So basically, that would be our definition of a pseudo-rotation. This is a diffeomorphism, a smooth diffeomorphism of the disk, which preserves the area orientation, and with just zero, with just one periodic point. So such diffeomorphism always has a unique defined rotation number, which is irrational. And so let's give maybe some examples. So of course you've got rotations of the disks, rigid rotations, and all their conjugates. So this, where H is area preserving. And you've got the very important Anosov-Katok examples, which are pseudo-rotations which are weakly mixing. In all this construction, the rotation number, in all this Anosov-Katok construction, the rotation number of F has to be Liouvillean. And in that case, F is rigid in the following sense, which is this one. You've got a sequence of times such that the qnth iterate of F goes to 0. So this is the notion of rigidity. So in all these examples, F is rigid and hence not mixing. But they are weakly mixing in the ergodic theory sense. So now,
the question is, of course, whether all pseudo-rotations are rigid. And rigid in the sense there is an iterate that converges to identity. Therefore, they are not mixing. So it's a simple question. You know that circle diffeomorphisms, for example, are rigid because there is an iterate that converges to identity. But they are not rigid in the smooth topology. Yoko's constructed counterexamples. C2, no iterate converges in C2 to identity. He has some special circle minimal diffeomorphism with this behavior. But pseudo-rotations may have more rigidity than their cousin, one-dimensional cousin, because of this area preservation. Of course, it's two-dimensional, but still has some extra constraint. This is related, to find a solution to this problem is related to control, an a priori control on the growth of a pseudo-rotation. there are results by Bramham, a fundamental breakthrough. He showed that when the rotation number of pseudo-rotation is very Liouville, then pseudo-rotation is actually Anosov-Katok in a weak sense, and it is not mixing. We answered this question in the analytic situation. We bridged over all angles by introducing KM theory to treat non-Liouville numbers. We still had a gap to fill, and we used something like Bayesian theory to say that if the growth of the derivatives was too big, then there would be a hyperbolic fixed point. Now the growth of the derivative cannot be too big, and we can have a bridging between KM theory that applies for Diophantine or Bruno condition and show you rigidity plus Liouville behavior. It's some things about surface homomorphisms. When they are very Liouville, they are rigid. So we conclude that real analytic diffeomorphism of the disk cannot be mixing if they have zero topological entropy using the Franks-Handel theory. Then a natural question is, are all pseudo-rotations Anosov-Katok? Are Diophantine pseudo-rotations Anosov-Katok? What about real analytic? Why? Because if the angle is Diophantine and it's a pseudo-rotation, by Roosman theorem, locally you are conjugated to a rotation. You have a small disk around the origin on which you are linearizable. Our theorem proves that you have iterates that converge to identity. So theory of renormalization can be introduced, similar to what Hermann and Yokos did to treat the global theory of circle diffeomorphisms. So you have some kind of global theory that is probably possible, because you see, for Diophantine angles, you know by Hermann and Roosman that if you are close to the rotation, you will be integral. Okay? This is by Km. For very Liouville, you know that you have iterates that will be very close to identity. So in both situations, if you are close to the rigid rotation, you will be, in some sense, your model will be the rotation, at least after conjugacy and iteration. So a renormalization theory points its nose, and then Raphael and Arthur did take advantage of this and succeeded in showing something that is a semi-global result, and that says the following. I almost finished, just 30 seconds. You say that pseudo-rotation is almost reducible if you have conjugacies that brings it close to a rotation, okay? And then you want to show the following, that if the pseudo-rotation is universally, some universal constant epsilon 0 close to the rotation, then it is almost reducible. This is like a result that would be similar to the expert with, say, Eliasson, semi-global conjugacy reducibility result on cocycles, quasi-periodic cocycles. So they managed to prove that when you are sufficiently close, but it's, why do we call it semi-global? Because this epsilon 0 does not depend on rho, okay? In particular, when the number is Diophantine, you have a global reducibility result. Global, semi-global, I mean, there is this epsilon 0. But still, epsilon 0 does not depend anymore on rho. Remember, by Roosman, you had a theorem, but the closeness had to depend on rho. But now when you have a theorem that tells you If I am close to this guy, I will have some result. And if it holds for all rotations, you expect a semi-global result. And that's what they got. Okay, I don't know, Raphael, you want to add something? But
no, it's okay. I guess,
thank you very much.
I guess we have to free the audience. So.